Hello, my name is McGuire Hodson, and this is my lab report for Lab 3, Black Hole and Orbits. The purpose of this lab is to determine the mass of a black hole by analyzing the motion of a star orbiting it and to simulate the orbit of a spaceship. The lab is based upon Newton's second law of motion, which states that force is equal to mass times acceleration, and the law of universal gravitation, which states that F equals g m1 m2 over r squared. The first computational model that was made using VPython depicts the trajectory of a star orbiting a black hole and the estimated mass of the black hole at each pass through the calculation loop. The second model displays the orbit of a spaceship around a planet and its moon. The first model showed the average mass of the black hole as 1.03 times 10 to the 34th kilograms. For the second model, the initial velocity of the spaceship was set at 1,000, 4,000, 0 meters per second. Both computational models include the effect of gravity, Newton's second law, and the net force formula. The formula for net force is dp times dt. The assumptions for the first model are that the star moves in a two-dimensional plane, that the only forces acting on the star is the gravitational force from the black hole, and that the mass of the star is constant. The assumptions for the second model are that the moon follows a circular orbit, the spaceship is affected only by gravitational forces of the moon and the planet, and that the planet does not move in response to gravitational forces from the moon or the spaceship. The models are used to simulate orbital patterns and experiment with varying parameters. The graphic on the top shows the law of universal gravitation, and the animation on the bottom demonstrates Newton's second law. In the first model, the system being analyzed is the star and the black hole. In the second model, the system is the planet, the moon, and the spaceship. In both models, the surroundings are the rest of space, which do not affect the systems. For the first model, the initial conditions set are that the change in time is 0.00001 seconds, g is 6.7 times 10 to the negative 11, delta t is 86,400, and t is 0. For the second model, the initial conditions have the same value for g, a mass of the planet as 8 times 10 to the 27th kilograms, a mass of the moon as 6 times 10 to the 25th kilograms, and a mass of the spaceship at 7 times 10 to the 12th kilograms. For the second model, delta t is 60, t is again 0, and t max equals 60 times 700. In the first model, the mass of an unknown black hole is estimated by analyzing the motion of a star orbiting it, which is done using the second law of motion and the law of universal gravitation. The second model's objective is to determine the velocity needed for a spaceship to successfully orbit a planet and its moon. This is done through carefully adjusting the velocity and applying both of Newton's laws. And so this is the code for Model 1, the relevant segment of the code, and this is the relevant segment of the code for Model 2. So the data I obtained for the black hole mass was that it was 1.03 times 10 to the 34 kilograms. And for the second model, the initial velocity that I set was 1,000, 40,000, 0 meters per second. And so the mass of the black hole was at an intermediate size compared to other black holes in the universe. And for the second model, even after 700 hours, the spaceship did not manage to crash into either the planet or the moon, meaning that my model was successful. And so this is the output for Model 1, and this is the output for Model 2. So, the net force is equal to the rate of change of momentum. This means that the force acting on the star due to the black hole directly affects how the star's momentum changes over time. The force acting on the star can be broken down into parallel and perpendicular components relative to its motion. The parallel component corresponds to the change in momentum, while the perpendicular component alters its direction. If you wanted to predict the motion of the entire system, you would need to include the effect of all of the gravitational interactions between the object, which include many such interactions, such as the gravitational force on the planet from the star, the moon's gravitational effect on the spaceship, and the black hole's gravitational effect on the planet and the moon. Although the spaceship's orbit was close to a figure 8, as was expected, this was not quite the case. This is due to many possible sources of error, including an initial velocity that is too large or too small and inaccurate force calculations. The estimated mass of the black hole may have been inaccurate because external forces are ignored, and the time steps may have been too large. Despite the errors in the experiment, the overall orbit of the spaceship was consistent and it did not crash into either the planet or the moon. In the first model, the mass remained consistent throughout each time step. Overall, this lab provided valuable insights into orbital dynamics, numerical simulations, and the role of gravitational interactions in celestial mechanics. The results demonstrate the limitations of classical physics when modeling space.